Okay. By the way, I got a new headset. So this headset is new. I think it sound is better. So I hope you feel a better sound quality. Let me know if it's worse. So I still have the old one. So if you prefer the old headset, then I could go back to the old one. Let me know. Okay. So let's think about the critical value approach. Um, Compared to the two-tail test, one-tail test has only one critical value, right? Two-tail test had two, which is represented by this sign. Plus minus is together, so the hypothesis value and plus minus something. And we have to change two parts. First, there is only one critical value, so either the sign should be plus or minus. And it's obvious, when you reject on the upper side, it should be plus. When you reject on the lower side, it should be minus. It's obvious. And then also, this part changes. Its idea is the same. Earlier in the previous T-statistic approach, when we studied the T-statistic approach, we used z alpha over 2 for the two-tail test because the error probability can arise from either side. But now we are considering only one side, so the whole alpha probability is used without splitting it because there is only one side, right? So these two are the differences. And then rejection rule is it's the same, right? Once the critical value is given, the idea is the same. We are going to reject the null hypothesis if the sample average is beyond the critical value. The critical value is a threshold cutoff, right? If it goes outside of that, then reject. But it depends on the direction now. So upper tail test rejects the null hypothesis if the sample average is larger than critical value, and lower tail test if smaller than the critical value. So the way you calculate the critical value changed, and the rejection rule changed in the sense that you have to think about the direction. It only considers one direction, but general idea is the same, right? Okay, and then like z alpha over 2 was used for confidence intervals and two-tail tests. Now you must be familiar with those numbers. We have used those numbers many times before. So the idea is because we treat both sides equally. So the overestimation and underestimation, positive errors, negative errors are equally likely, so they should be treated equally. That's why we split alpha into alpha over 2, but now we don't. We do not treat them equally. We only care about one of them. So alpha is not split. And let's compare for the three most common significance levels, 10, 5, 1, z alpha over 2 was given by these values, right? These values are what you used for the confidence intervals and two-tail tests, right? But now, even if the significance levels are the same, just because I changed the test to one tail, those values should be changed. So, by the way, it's interesting. 1.64 was used for 10% significance level because 10% was split into 5% on one side and the other 5% on the other side. So 1.64 actually represented top 5% or bottom 5%. But now this number is used for 5% because exactly that's what we need. 5% only on one side, top 5% or bottom 5%. So you can find the relationship, but in general they are not related to each other. So those 6 numbers are really commonly used in many examples, exercises in practice. So you may see them quite often. Okay, then let's come back to the example and think about more detailed numbers. Suppose that we set up our testing. We are going to reject the null hypothesis if you find that the actual amount of iced coffee is too small. So you randomly collected 100 iced coffees and their grande size, and their sample average was slightly lower than the 16 ounce amount. So if it was greater than 16 ounce, then that's it. That's totally fine. But now, because it's smaller than what it should be, so you have to worry about what's going on, right? You have to think about what's going on. The difference of 0.4 ounce could be just an error, like a measurement error, or an intentionally, the Starbucks is intentionally serving less than what it has to serve. So this process, the hypothesis testing process, will determine whether it is a random error or not, intentional cheating. So we are going to use T-statistic and the p-value and the critical value approach one by one, just to show you how we can carry out one-tail test. But the basic idea is the same as two-tail test. Just remember, we are rejecting on the lower side. So now we are rejecting on the lower side. So first, the T-statistic, no difference. So difference between, our observation is 0.4 ounce lower than what it has to be. So minus 0.4 is now standardized by the standard error. Then it will be minus 1.33, which is the T-statistic, right? And this T-statistic is used also for the two-tail tests. And then given this T-statistic, the p-value is the probability on the lower side of that, on the lower side of the T-statistic. So if you calculate probability of standard normal distribution smaller than minus 1.33, you get 9.18%. So the p-value is 9.1%, and the decision rule is based on this. If you use this p-value, it's clear, it's smaller than 10%. So you are going to reject the null hypothesis if alpha is 10%. But if alpha was 1 or 5%, it's sufficiently large, so you do not reject the null hypothesis. So the decision is based on your significance level. This is the p-value approach. Okay, now the T-statistic approach. Remember, rejection rule is like this. We are going to reject if T-stat is smaller than the negative of Z alpha. So of course, like a little bit of there is a margin on the negative side. So you should be sufficiently negative to be rejected. And T is minus 1.33. Then the cutoff, the thresholds are 1.28, 1.64, 2.33. Of course, you have to take negative minus of them. Then again, if alpha is 10%, then T-statistic is smaller than minus 1.28. So you have to reject the null hypothesis. However, on the other cases, you do not reject. Minus 1.33 is less than those margin, right? This is the margin you allow for error. So it does not matter, so you do not reject the null hypothesis. Finally, the critical value approach. Critical value is now located on the lower side. So you use minus sign, only the minus sign, and again also alpha over 2 is replaced by alpha because you are considering only on one side. And then plug in the numbers. If you plug in numbers, this is 16 ohms, and Z alpha, I gave you the numbers in an earlier page, and standard deviation and sample size, you know what they are. So if you calculate them, you get these numbers. But the sample average was 15.6 ohms. So when alpha is 10%, your critical value is 15.161. So if your observation is lower than that critical value, you are going to punish, right? Punish that coffee shop. But at 5% or 1%, you are more generous. So your cutoff is much lower, standard is much lower, so 15.6 is okay, like in this standard. So as you see, I used 3 different approaches, but the conclusions are the same. They should be the same. Basically, they are mathematically identical, so it doesn't matter which approach you use. And as you can see, the idea is the same. When you reject and how you can find critical value or T-stat or p-value, those intuition is quite similar, nearly the same as two-tailed test. Just it's tricky. We are considering only on one side. So just think about which direction you are going. That's the only difference, I would say. Okay, then now so far we considered a lower tail test. Now I wanted to show you what happens if you have an upper tail test. So I made up a related but a different example. So now iced coffees must be served or ice must be stored at a temperature of 40 degrees or lower, like in Fahrenheit, of course. So then now you are going to punish Starbucks if the temperature is too high. So iced coffee higher than 40 degrees is not cold enough. So you punish them. Just a made up example. Of course, it doesn't make any sense in reality. Just I wanted to give you an upper tail test example. Right? And here, so you say, suppose that you visited 100 coffee shops and you measured their iced coffee temperatures and you find the sample average was 40.7 degrees, which is again slightly higher than this cutoff standard. So then is it a problem or not? Is it a problem or is it a random error? So that's our question. And I assume the standard deviation is 4. Sample size is 100. And then in this case, I want you to calculate the p-value first. Remember, we are doing an upper tail test, so we reject only when x bar is too large. So use that direction when you calculate the p-value. Of course, you first have to calculate the T-statistic, and then you need to use a standard normal distribution calculator, Excel. And so pause the video and calculate this. Okay, the answer to this question is approximately 4%. So first, the T-statistic is calculated this way. The difference between the observed temperature and the standard temperature standard, their difference is 0.7. And 0.7 is standardized by the standard error, standard deviation divided by sample size square root. So the T-statistic is 1.75 if you calculate this, and the p-value now is calculated in this way, only on the upper side because it is an upper tail test. In our previous example, we considered lower tail test. So p-value was defined by the other inequality, but now it's greater than. So probability, if you use a calculator, you will get 4%. So 4% is the p-value obtained from this data and from the upper tail test hypothesis. Okay, then now if you take the critical value approach, what is the critical value in this case? We fix the significance level at 5% and the data are the same. In this case, what would be the critical value? Of course, remember, again, it is upper tail test, so you are considering the upper side. So try to calculate the critical value by yourself. I'm going to give you the answer in the next video. So before watching the next one, please work on this question. See you later.